Hello, everyone. My name is Molly Halsey, and I'm the event specialist here at EDB. I will be your host today for our webinar, Application Development and Database Choices, Postgres Support for Non-Relational Data. Today, I'm joined by Bruce Momgen, Vice President and Postgres Evangelist, and Tom Kincaid, GM from Second Quadrant. Before we get started, we're going to jump just into a few housekeeping items. Next slide. Perfect. This presentation is being recorded. We will be sharing the recording along with the slides after the broadcast. The lines are currently muted. If you have a question, please feel free to submit it in the question panel. Today's session is scheduled for a full hour. We expect the presentation to last some of our time, and we will allot any of our extra time for Q&A. If we do not have time to address all questions, we will follow up afterwards with any attendee whose question was not answered. Now, without further ado, I hand it over to Tom and Bruce.
Okay, thanks very much, Molly. Bruce, great to be doing this with you. Here, first Second Quadrant EDB presentation together. And we'll be talking about Postgres, why it's loved by developers, and while it's a great choice for non-relational as well as relational applications. So this is a real honor to be doing this with Bruce. Bruce actually introduced me to Postgres many, many years ago, and I run the Boston Postgres Users Group, and it's a great passion of mine. Bruce, any opening comments for the team out in video land?
Did we do webinars before, Tom? Is this our first one together?
I believe this is our first one together.
Wow.
I think we've done classes together before live, but I don't think we've ever done a webinar together. So.
Oh, this will be good.
All right, so here we go. Okay, so we're going to talk a bit about why Postgres has won, while it's the choice relational database and how it's growing, who's adopting it. And then we're going to get into some non-relational techniques with Postgres, a bit about document-centric applications. We'll be doing some things about geographic information systems. Lord willing, we will do a demo during that particular section. And then Bruce is going to talk a little bit about data, business intelligence, and some elements of using Postgres at the center of your database. So we won't hit all of these in any great depth, but we want to give you a sense of the flavor of what Postgres is capable of doing beyond using it for relational applications. Bruce, any additional comments on this?
You know, it's kind of funny, Tom. You would have thought we would give this type of presentation all the time, but you know, it's sort of like when you're living with this technology for so long, you just get used to a lot of the stuff it has, right? It's just like, oh yeah, we have GIS, and oh, you know, we can do all this other stuff, and oh yeah, this problem is easy solved with this other thing. But you don't understand somebody coming from the more traditional relational world, kind of coming into this and saying, whoa, where did that come from,
Yeah.
right? So that's what this talk really is sort of a stepping back, pretending we don't do this all the time, and actually come at it from a perspective of somebody who doesn't really work with this, and
the think different talk, right? Think different, right? Well, about Postgres.
Think different. Yeah. The joke was the original title, I think, for this one was, "This is not your grandfather's database."
Right. There you go. All right, yes.
That was a working title, yeah.
Okay. Maybe that title will come back in a future implementation of this talk. All right, so on to Postgres. So we're going to talk a bit about the statistics behind Postgres and how it's won. I'll give you a little bit at the high level marketing front, and then I'm going to have Bruce dive into some of the community elements of things he and the broader community have been able to accomplish over the years. Okay, so let's get started. So some data. Just some people like data. We're a presentation about databases. We should have a little bit of data. So DB Engine's Postgres won DB Engine of the Year in both 2017 and 2018. That's across 343 different databases. Postgres won, and it was chosen based on how people react to it, how much people love using it. Then it just kind of gets a little sense of things. If you look at that graph on the left, it'll talk about the most commonly used databases, and you'll see that MySQL is first and Postgres is second. That continues to go up year over year. If you look at the most loved databases, this is according to the Stack Overflow survey. They surveyed developers, and which database do you love the most? Well, Postgres came in second, but in terms of relational databases and even general purpose databases, object relational databases, Postgres is, number one and growing every year. So this is not, this is this claim that we are the most loved relational database is backed up by data. And then, as you can see, there's the popularity as the DB engine's popularity continues to grow. So Bruce, you've been at this with Postgres for a while. How's it feel when you see these kind of numbers and this kind of?
Yeah, when we started you're talking about the graphs. I have a graph that I often use where I talk about the adoption of Postgres, and of course, being with this for 24 years, we started out way at the bottom, right? We weren't on this chart, right? But what was really interesting for me is that we always had a steeper adoption curve than anyone else. And if you have a steeper adoption curve than anyone else, eventually you will overtake them. It may take 20 some years, but I think that's one of the key things is just getting a steady adoption, not losing people, providing technology that's really ready for the market, and just continue to do that year after year.
Once they go Postgres, they don't go back, right?
That's right. Very rare. Very rare. There's one company that did leave it for one specific project, and it caused a huge stir, and there's blogs about it, and I kind of, somebody said, "What's your comment on that?" I said, the fact that somebody left our database is news, right? Somebody leaving Oracle or MySQL, that's not news at all, right? So, I'm going to take that as a win.
Gotcha. Once every now and then. All right, good. All right, so just to kind of give all the major cloud vendors, this has really happened in the last, I would say, 5 years. They've all adopted, they all have Postgres offerings. So it's not just us. Everybody realizes that people want it, they're using it. And if you're going to have a database as a service and not offer Postgres, you're really not going to have a very viable database as a service. So kind of getting along that. So Bruce, would you mind?
I was going to comment on the cloud thing. First thing, we should probably get Alibaba on there.
Okay, yeah.
They're obviously a huge provider in China. Second, Amazon had a big announcement yesterday that they're going to be open sourcing a fork of Postgres that has compatibility with Sybase and Microsoft SQL. So again, not only are they providing Postgres, but they're actually investing in Postgres, and they're sort of making it a strategic decision for their industry.
They're contributing. Yeah, they're contributing to the ecosystem.
Right. I mean, same thing with IBM, which has DB2, yet they're providing Postgres, right? So, and Microsoft has Microsoft SQL, but they're providing Postgres. I mean, this is just, you would not have seen this 10 or 20 years ago of somebody actually promoting a competing open source product to their own proprietary one. Would be crazy. Now you can't do it. You can't remain relevant unless you really embrace the open source relational.
Gotta embrace the world's most loved database, all right?
There you go. Yeah.
Okay. All right, so Bruce, would you take us through, I put together some statistics around the community. Would you mind taking us through this, since you live and breathe this every day? And
I kind of love this graph. As I said before, been at this for 24 years, and it is really weird. I mean, even going back to the adoption thing, it's sort of like, I was thinking about this morning, it's sort of like, you have a child and you change their diaper and you get them to walk, and you finally get them to kindergarten or school, and then they finally go to college, and all of a sudden they become president of the United States. And you're like, what happened? Like, why? I remember when, the person was a child or an infant, now they're president of the United States. Not that Postgres is the president of the United States, but the point is that when you're raising a child, you don't really think, oh, this is going to be, something, that's going to have, worldwide impact, or something that's going to have, a tremendous amount of longevity and really help to define the relational market. You just kind of raise the child as you raise the child. You do what's best for it. You try and you try not to make a lot of mistakes with the child, right? And you try and grow and tender it and make sure it's fed and make sure it's healthy and so forth. And that's kind of what this chart shows, that really for those 24 years, we have been putting out regular releases. We have been, you can see there's probably between 150 and 220 features that come out pretty much. This is a yearly release cadence. There's really no other relational database that does this, where you're putting out that many features in that yearly short amount of time. But again, it's because of the way the open source system works, because of the way that open source development happens. It's very incremental. It's very high reliability. So you can do this kind of thing. And proprietary databases, I think they kind of admit, really can't. It's just really too hard within an organization to put out this amount of volume
Yeah.
at high reliability.
Yeah. 150
And I think
plus
that's
features
a
a year.
great. Yeah, I mean that's, and I have to write those release notes, and it's a pain every year, I'll tell you. But it's because it's a lot of minutia. It's like, okay, this feature now does this thing and whatever. But I have to say the team that we have around the world and so many companies that are involved, both database companies, non-database companies, yeah, telcos and companies you wouldn't think would be involved are involved. And that's really the exciting part, is so many people kind of coming together and getting the best ideas from all of them every year into a release is a great feat. It's very similar to the success you see with all the other open source tooling out there. That process is just so robust and so efficient. And we're kind of the player in the database area that does this kind of open source development model, year after year for so long. And I think that's one of the reasons we've gotten that stature at this point.
All right, should I go to the next slide? More great
please.
things to tell. Okay, good enough. All right, so
again, the number of people who kind of work on the community, it's an open community. It's open development. So some people get confused between open distribution of software, which is what the Mongo group does and the MySQL group does, versus open development and open distribution, which is what Postgres does. So all of our development is not controlled by a single company. It's basically whoever wants to submit a patch submits it, and then somebody else improves it, and then somebody else improves it, and finally it gets into a release. And you can see the number of people who are involved in a yearly release, and I believe my boss helped to develop this chart, is increasing. We have a lot of really, really big companies that are doing that. Probably the biggest company involved is NTT out of Japan. They are, I think, Fortune 30, Global 32 or 36, something like that. So again, big companies involved in helping. But again, not just big companies. We have small consultancies in Austria that are involved.
yeah,
We've got a lot of activity. China's heating up. So it's an exciting place to be.
yeah. So that's pretty good. Over 150 features with 300 people every year. Well, all right, so the matrix. Okay, so talk us about some of, I think things have gotten, we're not just, these aren't little trivial features, right? These are some of the things that got a little harder. So
yeah, as I said a couple minutes ago, Postgres is really big on incremental development. So instead of having a big cloud release that happens, after 3 years of development, or a big security, enhancement release, or a big release that sort of targets data warehouse, we're improving things every year. So parallel query is improved in 9.6, but continues to be improved. Even in Postgres 13, we had parallel query improvements, I believe. Partitioning added in Postgres 10, 11, 12, and 13 continued to improve partitioning. Stored procedure languages in 11. Just-in-time compiler, there's still a bit of development to go there. Pluggable storage, we're just really starting with. Again, you can see in 12, we've improved partitioning, the scaling of partitioning. And then 13, you see more things again related to sorting and performance. So it's kind of it's not like a big bang that happens every 5 years. It's a very incremental 1-year cadence kind of thing, and feature arrives in 1 year. Next year gets improved. Next year gets improved. Probably 3 years until the feature kind of gets to completion, where it scales linearly across all of our workloads, where it has all of the features that are possible and all the performance enhancements typically. So that's one of the great things, is we don't develop something and stop. We develop something and then continue to improve it. And that's partially because of the way the development model works.
Okay, so just kind of summarizing, because we're about to get into this, is you're not your grandfather's database section. So, but summarizing about your grandfather's database element, strong support for SQL. I have a chance to talk to a lot of people who got early involved in Postgres. both Simon Riggs and Bruce, I said to him, what got you involved in Postgres initially? They both said to me, the optimizer. And so it has a phenomenal optimizer for relational queries and an advanced feature such as window functions, some of which we're going to talk about later today, fully ACID compliant. And it's the source for many commercial relational databases today. And whether it's the source or a part of the source or some element of it, we'll just talk about, I have a slide on that in just a moment. Okay, so these are a number of vendors who have leveraged Postgres, meaning they've created a fork or they've created an extension, but Postgres is part of their business. So it's not just Postgres itself, it's a larger ecosystem where certainly EDB has a very advanced version of Postgres with Oracle compatibility and enterprise features. And I'll let you read through some of the others. But any other comments on this, Bruce? Or?
No.
All right, good enough. Okay, so we're now into the heart of the think different portion of the presentation. Okay, so it was designed from the start to be extensible. All right, so you hear Postgres, the object relational database. So what does that mean? Well, it really means that it has the ability to add additional types and non-scalar types. So types that don't fit into nice unique things like integers or real numbers or strings, but all sorts of types. And one of the extensions that later became part of core is JSON. So JSON is a natural fit. It kind of became over time, it kind of replaced XML as the language of the web, or the data interchange format of the web. I guess it's not really a language, it's more of a data description, and it's fits very well together with SQL. And it's also been it's this concept of creating key value store lookups. I have a key, I look up and I get the JSON value out, and I use that in my application. Goes all the way from my Node.js middleware out to my web browser, and it works great. It's a sense of I store the data the same way the application uses the data. Well, that works out great in Postgres because of this concept of extensions. Bruce, any comments, or should I go right to the next gamut here?
No, I think it's important for people to kind of relearn their perhaps aversion to extensions with databases, because the typical, my experience with relational databases that aren't Postgres, when they typically add or something, it doesn't really work the same as the built-in stuff. So it doesn't back up the same. It doesn't list in the catalogs the same. It doesn't sometimes even optimize the same.
Transactions behave differently.
But Postgres, because it was designed, but because Postgres was designed to be extensible, every native type that Postgres has, like integer, varchar, use the same extendability mechanism.
Mm-hmm.
So effectively, when you're adding JSON or GIS or data warehouse types, you're doing it as the same way a built-in piece would be done. So all of these sort of non-relational parts of Postgres, which in others, like full text search, which in a lot of databases are this extra thing, which maybe isn't transactional, which has to maybe be backed up differently, which doesn't sort of follow the same syntax. In Postgres, all of these things behave just like the normal data types. So when we started with Postgres, this extendability was a real pain. It was really hard to get it working. It was had a lot of overhead. It had a lot of bugs. But those are the early years back in the late 90s. Now, this extendability is at the core of what Postgres does. And it's really at the core of what allows Postgres to handle the workloads of today. Not necessarily the workloads from, order entry applications from the 1980s, which is traditionally what relational systems have done. Yeah.
Okay, so now let's dive into some specifics around JSON and how it might work. Okay, so all I've done here is I've created a table. It's called semi-structured data, and it takes as one field of type JSON-B, which is, Bruce, I understand that to be parsed and processed JSON, so that we're not constantly, we can index and do all sorts of other things. We're not constantly loading and unloading strings. And then I create a JSON string and I just insert it into the data. And there you go. Very simple. I've inserted it. Now I just have one field, but an important thing to point out, and we'll see this later. I guess we don't have an example of this later, but I could have other fields. I could have my key. I could have a timestamp to say when it was inserted as regular relational data fields together with this JSON-B field. All right, we're going to talk, we'll show you some things you can do with JSON-B. So there you go. I've inserted that. And now let's go to the next slide. And I wanted to just provide an example. JSON has 5 basic types: strings, booleans, numbers, objects, arrays of objects. And those are all supported within Postgres. We have functions and features to support all of those. There are no limitations. We support the whole thing. Everything is great. Okay.
The thing I should point out there, Tom, is that you basically, just to reiterate what you said, you have a JSON field, okay, which inside a JSON-B field, I'm sorry, but inside of it, you have individual keys and values inside that one relational column, okay? And the system knows which ones are strings and which ones are numbers and which ones are Booleans, okay? So it knows inside that JSON column what values for which keys have which types of values. And you can do all sorts of unusual things.
That's a good point.
Plus, each row in that column can have different keys and different values.
Right. Good.
So
Good.
there is not a traditional relational layout to this. It
Right.
can be whatever that particular
just
field wants to put in there.
Yeah, we're not just stuffing a string into the column. It's actually understanding what's in there. And yeah. Okay. So I do that. Okay. So to Bruce's point, this is a two entirely different values. Nothing like one like the other in the column. So I can just take that object I showed you and stuff it into the same column, and it's semi-stored. So 2 completely different objects stored in Postgres. Okay, no big surprise there, is based on what we've covered so far. But just a couple of helper functions relative to Postgres. If I have a product table, I can select. I can do a select all from it, but I can also convert it to JSON and select specific fields. There are just dozens of little tricks like this you can do in Postgres. So this is very helpful if I'm developing a web app and I need the business intelligence applications to be able to access the backend data store. I can keep it all relational. When my web app needs a JSON data, a subset of the data, I have the helper functions to do that. And there's just dozens of these things. And this is great because people who are developing these applications, as Bruce said, because of the Postgres development model, they say, boy, wouldn't it be great to have a feature that did this? They may develop the feature and the feature gets contributed, right? And somebody like Bruce reviews it, commits it, and everybody benefits. So Bruce, any other favorites you have in terms of these helper functions? I'm going to show the combination of querying both relational and doing a join with the JSON in just a moment. But any other favorite JSON helper functions or tricks?
Yeah, look at the next part.
Okay,
let's take a look at the next part, because when you start to mix the JSON with the SQL, it gets really interesting.
Oh, right. Okay.
I think.
Yeah. Why don't you take us through this one then? Go ahead. So.
Right. So we, there's 2 ways in my mind. There's 2 ways of using the JSON field. One is to basically just take the JSON, put it into the database, and then take it out of the database. Or as Tom showed the previous slide, take some relational data, take it out as JSON. So in those cases, you're effectively, the JSON is an island, right? Either the JSON exists individually within the data, you just put it in and take it out, or maybe you just export your data as JSON. Where it gets really interesting to me is where you have some data that is relational and some data that is JSON. So in this case, what we're actually doing is we're inserting, we have these 2 rows in the JSON, which, one's a phone and one is a spouse, I guess, or one's an individual.
We'll call it a spouse is a good one. We'll call it a spouse is a good, yeah. Yep.
Mm-hmm. Right. Well, no, it looks like their spouse is null, so they're not married, right?
Okay, got it.
So, yeah, that's what I'm guessing. But there's no name. I don't know what their name is.
It's a person. It's an individual. But we have a phone and a person.
Phone and a person, right? And that's a great example of putting this different things in different rows. But then we can mix that. So in the query at the second part, we're actually taking, we're querying the semi-structured objects table, and we're actually taking the key called brand. That's what the dash double
Mm,
greater than sign is. And then we're saying, it is that equal to the string Acme? And if it is, give me the name, the key, the
mhm,
value associated with the key name here.
right.
And that's why the Apple phone, it skips over our person, because they don't have they don't even have a key called brand, let alone a value for that
Yeah.
key of Acme. So you can mix relational and non-relational in this case.
Now that's great. So the idea is that now I have a whole other way of accessing JSON
Right.
data based on the way I've been developing my app for so far. Okay, great. Okay, so we'll actually take this one step further, and here's
Yes.
we're doing a join with that semi-structured objects together with the product table,
Yep.
and but that's really quite nice because part of the join has JSON constructs on it, the other part has SQL constructs on it, and
Yep.
this is just an incredible, a very powerful thing in the sense of there's all sorts of analysis I can do on the JSON data that wasn't available to me previously, and even updates and transactions and terrific thoughts. So do you have any additional thoughts on that, Bruce? I know this has kind of covered some of it on the previous slide, but I thought this even taking your example further where I can
Yeah,
query.
this is to the next level, because normally when you're the whole mantra of NoSQL was unstructured data. Well, after a while, people really kind of realized that unstructured data is pretty much useless data because
Mm,
there's no structure to it. How do you know where it is? How do you know what the keys are? How do you know where, it's just, and that's where you got a lot of these data silos in NoSQL, where you started putting data into this silo, but you could never get it out because you could never figure out where it was. So where I think, um, you even NoSQL's kind of gone back and forth between calling it unstructured to now calling it semi-structured. Where I think this really highlights is the concept of having a mix of relational and NoSQL or JSON type of data in the same data row. So particularly when people are creating data models, they always they like the relational, some of the relational parts of the schema design, but they don't want to be held down to fixed columns.
mm,
So in a product table, for example, you're always going to have a product name, that's like, in a product ID.
mm,
Those have to be there, and you typically don't want them to duplicated. You want to be able to join on them and so forth. So typically, when you're going to design a schema, you're going to put the things that you want to have relational integrity on, things that you want to be unique, things that you want to join on. A lot of times, you're going to put those in the relational part of the row, and then you want this additional part of the row sometimes for things like voltage and weight and certifications and color and style and
yeah.
waistband size, right? That aren't going to fit into into a relational model, but you want to record that
Yeah.
information,
And
and
they may
mixing those two together is good.
you may or may not want those data fields, right? Sometimes you want them, sometimes you don't, and this gives you that flexibility. Yeah.
And historically, what people would do is that you'd have a table with 110 columns, and then you added a product that had a marine certification, right? So then, well, I got to add a column for every row now
Yeah, yeah. And
to
that's
have this marine certification, right? And you'd be perpetually having to modify your model for every new thing you had to track, or you'd store it in plain text, and then everyone, it would be all be different,
yeah,
right? So what I think the real power is not only for JSON getting it in and out, but having that flexibility of data model at the same time, having the ability to place to do some of it in a relational way, depending on what your data needs are.
yeah. All right. Well, fantastic. Okay, so let's talk a little bit about comparing this. It performed very well. Now, this is a benchmark against the community version, but a benchmark we did, but you can download and get it. And Postgres performs very well against Mongo, and actually in many cases beats Mongo in dealing with documents, JSON objects. There's the place where you can go get it. to share a little bit of the data. In this particular workload, it well outperformed for Mongo. So it's not that it does this at a huge expense. So you get all this functionality at a huge expense, and you still get all that goodness of relational access and asset properties. So download it and check it out for yourself. All right, I'm going to pick up the pace slightly because Bruce had coached me a little bit about where we want to be on time. So I'll get there. So we'll get into our next non-relational element of this. And okay, Postgres is an extension, and it's one of the most popular. Just by adding this extension, you have one of the world's most popular geospatial databases, and gives you all sorts of other ways to access and combine data with relational data. So let's get to that. All right. So Postgres, that's all I do. All of a sudden, it doesn't come right out of the box. I hit create extension Postgres. The extension gets created. I did it, and that takes about a second. And then all of a sudden, as a result of that, I now have one of the world's most popular geospatial database built on well-established industry standards in the geospatial world, together with another database, Postgres, built on the SQL standard and many other standards. So fantastic. There we go. All right, Bruce, I'm going to bring you back to give out some examples in just a moment. So we'll get to that section in just one sec. So there are many here, and this is not just that I'm saying it. These are geospatial applications that support Postgres. All the world, ArcGIS, one of the most popular geospatial applications in the world, supports Postgres and drives a lot of the Postgres development. But again, a whole other world, just this single extension. So what does Postgres enable us to do? So Bruce, I liked your story about, you were telling me earlier about fraud, credit card fraud, and geolocation. Do you want to I'll let our viewers read these examples while you tell us about your example.
Yeah, sure. So I did an artificial intelligence presentation a couple weeks ago, and when I started to look at using AI for fraud detection, I started to realize that there is a spatial component to that particular AI example, and the spatial component is typically something like, what is the distance from the vendor location to the billing address of the credit card holder? For example, if there's a huge, the longer the distance, obviously, the more likely potentially it's a fraudulent claim. Another question is, what's the distance between the last transaction on that credit card and the the current transaction? If there's a huge distance between the two transactions and they're only an hour apart, it's possible there's fraudulence. Again, that's not a clear indicator, but it's something you may want to measure. And typically when people are using relational systems, they kind of eliminate the thought that they can interact with spatial components in their data. It's just not there, right? They think of money, they think of item counts and billing and all that other stuff. But with GIS, you can take your data and make spatial measurements or spatial calculations based on your data. And that now gives you a whole new way of calculating or of making use of your data that you probably didn't have before. So although these examples we have right here may seem kind of trivial for a database, there are real practical applications to having GIS data in your database where you can make calculations. How far is this zip code from this other zip code? How far, are these two plants? What is the area of a particular, zone? All of these type of things can be very easily done in GIS and give you additional capabilities that you don't have to leave the database to do. Typically, you'd have to go outside the database to render an image or to make a calculation like this. With PostGIS, you don't need to do that.
All right, so just kind of building on that. So once I've added that extension, a couple things happen. I get a bunch of new types, and we're about, depending how you count, between 4 and a dozen. And I get a number of, I guess, around 1,000 new functions that can all be part of my analysis. So I'm I have a table of interesting cities, and because of Postgres, I'm given the geometry type. Within geometry, I can specify it's a polygon, a point, and several other things. And this time I am specifying it is a point And then I also specify spatial reference ID. I won't get into that. Both JSON and Postgres are probably presentations or courses on their own, but effectively think of it as longitude and latitude points on a globe. We're going to transform that in a minute. I'm going to talk about the medium home value of these interesting cities and the city's population. And again, but the key point here is I'm adding a new type, a new column type, just like before, where Bruce talked about adding the JSON B column type. I'm now adding a geometry column type. And maybe some version of this presentation will have a table with both a geometry column and a JSON B column, and we'll do all sorts of interesting queries. So getting into that a little bit, if you want to, here's an actual query as opposed to just query. I want to know how far Bruce and I are apart from my interesting city. Bruce is in Philadelphia and I am in Boston. And this is all I need to do. I have these additional functions. Before I talked about the additional geometry type. Now I have some additional functions. And you'll notice I'm doing two things here. One is I'm doing a transform, and I'm transforming, there's a Postgres function to transform. I'm transferring my points on the globe to meters, and then I am doing a distance as a result of the transform. So I can answer these kind of questions. So Bruce, how far do you think we are apart? I think I know you know the answer. We practiced this a little bit, but for the sake of the audience, what would your guess have been?
Well, it takes me about 5.5 hours, so it's probably like 280 or 270.
Yeah. Okay. Right. So this is as the crow flies. So this is no roads involved. It's just sheer distance. So it's not that far. So 431,000 meters roughly. Okay. So
there you go.
I think that makes up. So that makes sense. Okay. So again, just a simple select to do a transformation. Now to get things a little bit farther along. Let's say I want to find. I want to relocate Bruce to Boston, hypothetically. Okay, and Bruce would like to live in a small city outside of Boston. He only wants to live 150 kilometers from Boston. So I want to find out all the interesting cities that are within 150 kilometers of Boston, and I want to have them sorted by the medium home value. But again, this is just like before. We were intermixing relational, typical relational data with JSON. Here we're intermixing typical relational queries or questions or analysis together with geospatial questions and analysis, all doing this in a single statement. Okay, so there you go. So if I do this, okay, I guess, is this the point where, yes, this is the point where, okay, do we have time for the demo?
Oh yeah, go for it.
All right. So I wanted to show a very interesting element of, okay. That's not. Okay, so here I have the query that I had back in the presentation. If I want to just run the query.
Oh, okay, now I see the PG admin, got it.
Yeah, okay, it just came up. Okay, so I ran this query and it gave me the output. So that's great. Now, a nice feature of PG admin is it's telling me this is a geometry column. So I can click on this and it actually shows me the result. I didn't have to add anything, and there's it. So there's the potential cities we may relocate Bruce to.
Wow, look at that.
So there it is. And so I actually saw Dave Page give this at a Boston users group, and I was just so blown away. So I'm happy to have successfully pulled it off here. All right, so now we will go back to our regularly scheduled presentation. Oh, it's going to want me to sign in. Okay, I am going to stop. Sorry this has happened, but I'll stop share just for a moment.
Sure.
I'll sign back into my. Okay. Almost there, sorry.
Mm-hmm.
All right, so Bruce, can you see my screen again?
Yes, man. Yes, sir.
Okay, so let's talk. So we've talked a bit about what we can do in the world of document storage, a little bit of what we can do in the geospatial world. Let's talk a little bit about some of the advanced features of Postgres that you can use for business intelligence. Okay, so Bruce, this is actually taken from momgen.us. Would you mind taking us through what we're trying to accomplish here? And then I have some thoughts I will share afterwards. So.
Yeah, so this query is from a larger presentation that's on my website, momgen.us. But this query was, I think, got Tom's interest because it's a use of common table expressions that is actually not part of the SQL standard. So the SQL standard defines a pretty rigorous capability for common table expressions. If you haven't used common table expressions yet, common table expressions are a way of sort of taking one query and using its output for a later query. So instead of having to run a query and store it in a temporary table or so forth, you're running a query and then you can reference that query later on. It's also very common for recursion. So if you want to walk a tree type of structure, you can use recursive common table expressions to perform that. But that's not this. This one is a little different. And it relates to an extension about the way that Postgres operates called a returning clause. Effectively, what you can do with common table expressions in Postgres is you can issue queries and use the output of those queries to issue other queries, and the queries don't have to be selects. So normally, if you're deleting an order, for example, you would delete the order and then you would get, the order ID, and then you'd have to delete the items of the order ID. And then somewhere else, you may want to record the deletion, that you deleted on a certain date, or so you don't lose the idea that you made the deletion. This does all of that in one query. Uh, the first line in red deletes the order, but it also returns the order ID. So you normally use the order, you have a text string that represents the order description. That returns an order ID. That order ID is used in the second red query to delete the items associated with that order. And the third query at the bottom, the insert, is actually inserting into the old order table to record that the order has happened. And the reason that's interesting is because this all happens in a single transaction, a context. So the visibility, if you're familiar with SQL, this is a repeatable read or serializable context type of query. So the visibility of the first red query, the second red query, the third red query are all the same. You don't have to return the order ID to the application. You don't have to issue a new query to delete the items. You don't have to delete or issue a new query to insert into the old orders table. You effectively are doing it in one query. So this actually for application developers makes it really convenient to be able to kind of chain things together and do them atomically as a single query without having to do a lot of, you know, round trips to issue separate queries up to the server. So that's this kind of a very advanced feature. Again, it's hard to start at this one because it's really complicated,
Yeah.
but you can get an idea of what Postgres can do.
Yeah. No, I think the thing that kind of really piqued my interest about this is I could write less code, and
Yeah.
I have less code to write, and I get better performance. Another reason why developers love this, right? It's and I can add other things. So, all right, thanks, Chris. Okay, tell us about window functions. What are some of the? I know this is a we got just a few minutes for window functions because we do it early. As you say, we want to have a little time at the end. So
Yeah, so this is again a query that's part of the last, it's sort of one of the end queries of a presentation. But effectively, the SQL standard does define window functions. I believe Postgres' implementation is the most standard compliant of all the relational databases. And it effectively allows you to do data analytics, again, very similar to the issue with common table expressions, where you normally have to issue a whole bunch of queries. If you're trying to generate a query that averages the salaries for individual departments and then compares those and ranks them or so forth, those are typically things that have to be done in the application. By using window functions, you can effectively do all that sort of aggregation by department in the database, and therefore you just get the results to the application. It's obviously more efficient to do it that way, and obviously, as you said, Tom, requires less code.
Great. Okay, so fantastic. So the most compliant window function implementation. That's awesome and great for analytics. So, all right. So I know that over the years that as we've been at the extensibility, we have a lot of index types, and I'll did a couple. But the fact that the GIN index, right, JSON data, we didn't talk too much about that, but these are different types of data require different types of index. And again, there was a different type of index for spatial data, for and then there's your standard B trees and hash. And are any other new indexes in our future, Bruce, or any indexes on the way?
Well, I don't see the Brin index listed here.
Oh my gosh, I didn't have that. Yes,
Yeah.
block range indexes. Yes.
Right. So that was introduced. That was introduced about 6 or 7 years ago. It is actually an index specifically designed for business intelligence, for
Yep.
scanning large tables with very small, compact indexes.
Yeah. And
The GIN index, as you said, is really great for JSON data and full text search. So the point here is that traditional relational databases mostly just have B tree and hash. And if you only have B tree and hash trying to handle things like GIS or JSON or full text search, becomes very cumbersome, because those index types are really special, are really designed for unique comparisons and for sort of handling where you've got a range of values. But when you have a lot of duplicates, for example, GIN really shines. When you need to create a lot of very compact indexes, Brin indexes shine. When you have a lot of when you're indexing a lot of values that have a lot of duplicate prefixes, SP just shines. So again, extendability in Postgres is not just at the data type level, but it's at the index level, it's at the language
Right.
level, which you're going to show, it's at the operator level, it's the aggregate level, it's at the function level, of course. So it's kind of across the board. And that, again, as I said in the beginning, has allowed Postgres to handle today's workloads much better than a traditional relational system.
Yep. And just while you were talking, I thought of even more indexes. We have partial indexes and covering indexes, and it's all it's great. So, okay, fantastic. All right, I'm going to go. Oh, there's Brin. Okay,
Yeah,
good
made
job.
it there, yeah.
All right, look at that, and we do right, all the things. Everybody. Oh well. Okay. We'll remember that for next time. Okay, first time. Okay. Okay, so I'm going to cover this quick because we can get to the last couple of sections. So we have a few minutes for questions. Okay, the Postgres through extensions has something called foreign data wrappers. Foreign data wrappers enable me to read and write data to other tables. And here is some server. I'm creating foreign data wrappers for Postgres, for Oracle, for Mongo, Hadoop. And then I have something like this where I can do queries and analytics across many different data servers, all appearing as Postgres tables. I can do update transactions. That's probably a separate webinar in and of itself, as are a number of these topics. But we wanted you, again, this is all helping you think different about Postgres, and this is not your others database. So Bruce, do you want to just talk a bit about the server-side programming languages and
Sure.
some of
So with the foreign data wrappers, we support over 100 different data sources, both read and write. So effectively what that does is it gives you a table on your server that looks like it's on your server, but it's actually in Oracle, or it's actually in Mongo, or it's actually in Hadoop. So it's sort of a virtual table, which exists not in necessarily, it can exist in another Postgres server, or it can exist in any of these other 100 types of data sources. Server-side languages, again, another area that Postgres shines. The ability not just to have one server-side language, which is typically what most relational systems do, but depending on the type of data you're working with, PL Perl might be a great solution. PLR, PL Python might be a great solution. PLV8 if you're working with JSON. PLR is great for statistical analysis. So again, depending on what type of data you're using, you can actually use a similar language, or you could use the same language as you're using at the client side. So if you're using Python at the client side, you could potentially have Python at the server side as well, and use the same language constructs in both places.
Great. All right, so we should probably have a conclusion slide, but summing it all up, it's a fantastic database. You get traditional relational data with transactions and ACID compliance together with all sorts of other data, structured, unstructured, geographic information, whatever you need, business intelligence. So Bruce, any final thoughts before we turn it over to questions?
Yeah, let's do the questions.
All right, Molly.
Yes.
So we have some questions along the way.
We do have a couple of questions. So for anyone looking for the resources on this Learn More slide, they've just been dropped into the chat channel if you're looking for that instant click. We did have a couple of questions. The first question was, can you index the JSON object for better performance?
So that's actually something we didn't cover, Tom. You and I
Yeah,
talked
I know.
about
We talked about it ahead of time, but didn't we
didn't come into the
poor execution. Oh well. All right.
So it's very good that you asked. Yeah. So, and in fact, it's actually good you asked at the end, honestly, because as I said in the previous slide, the GIN index is really ideal for things like JSON, JSON-B, and full text search. And the reason for that is that the GIN index is effectively an inverted index. So in a non-inverted index, traditional B tree, every key is in the index. So if you have 5 duplicate keys, you have 5 representations of that. Although that's changed in Postgres 13, typically for a traditional relational system, your B tree has 1 row for every matching row in the heap. For a GIN index, because you have so many duplicate references to the same word in full text search, so many duplicate references to the same key and potentially the same value in JSON, we specify the value once, and then in the index we represent all the rows that match that value. So you get these very compact indexes, much more efficient. So when you index a JSON-B column, we index every key and every value. You don't specify typically unless you create a B tree index. But if you create a GIN index, we're going to index everything. So no matter what key you're looking for or what value you're looking for in that JSON, we're going to use the index to find it.
So the answer is yes. We index it, and then we can actually do even more specific indexes, right, Bruce, beyond what you get by default with JSON-B. Is that right? I remember that was a discussion from yesterday. Okay.
Yeah.
Great. Another question we had come in was, what happens when delete from orders works, but delete from items fail?
So if you take a look at that query, the delete from orders is where we're doing the returning. Okay. The delete from items is not returning anything. So if you take a look at the way that you see the word source there at the top, not source, we have source and we have source too. So if you take a look at source, that's what we're referencing in the insert. So we don't care if there's no items for the order, we're still going to record it.
Okay, great. Another question we had was, is there ways to speed access tables with JSON, not querying by JSON column?
I don't know what that. I'm not
sure. I wasn't quite sure. Is there any chance to, why don't you have them send us an email? I'll post it to bruce.momgen@enterprisedb.com, tom.kincaid@enterprisedb.com. Sounds like we have to have an interactive discussion to get further clarity on what we'd like to.
Great. Another question. We have more questions. No worries.
Okay.
Another question we had was, do graph database features exist in Postgres, extension, and wrapper?
There's 2 areas that I don't think Postgres is very strong in the NoSQL space. As you may know, there are 4 types of NoSQL databases. There's key value, document, columnar, and graph. The 2 areas I think we're not strong is graph and columnar. Columnar you can sort of do. We have the Microsoft extension Citus, which can be added to Community Postgres, which will give you columnar. For graph database, I'm not sure what I would recommend there. You can use common table expressions to kind of walk a graph tree, but it's not quite the same as a graph database. And I'm not aware of anybody sort of providing a graph style extension for Postgres. So the answer is kind of no. I don't really know what I'd recommend. What you might need to do is use foreign data wrappers and connect to a real, a dedicated graph database for that kind of problem.
Okay, we have time for one more question. That question is concern over PL Python being unsecure legitimate? Does the function have unlimited access to the database server, such as dropping files and other activities?
The answer is yes. I was at a lunch with some some Postgres friends this week, and we actually ended up talking about that because they're a cloud environment, and they can't support PL Python U because and we actually went into the details of that. So PL Perl has an untrusted I'm sorry, PL Perl has a trusted container that you could run Perl in. PL-V8 also, because it's the V8 engine, and PL Java have this sort of trusted container where you can run these languages inside. Python, the Python language itself, does not have a trusted container. They had a trusted container for a while. They removed it because it wasn't secure enough. And I don't know of any work being currently done. There was some fork of Python that supposedly did it. I don't know what the status of that is. But unless Python gives us a trusted container, we can't give a trusted language. And the implications of that are that only super users can create these PL Python U functions, because giving that ability to a non trusted user would potentially allow them to do anything,
Right.
Including harm the database, which we would
Right.
not want to do.
Right. But it's actually that Python doesn't have a way to sandbox what it can do, whereas some other languages like Java do have that kind of ability.
Exactly. Sandbox is the term I should have used. Yeah. So
So-
when I'm saying trusted container, I'm saying sandbox. Python has it. Java has it. JavaScript has it. Python does not, and therefore we can't give the users a trusted version of PL Python.
All right. Well, Molly, I think you said we're at the end of our time. So thank you very much, everyone who attended the webinar. Bruce, thanks for sharing your insights together with me over this and doing our first webinar together. And Molly, appreciate your hosting. And we'll see you all, I guess, December 18th is the next webinar. Is that right? Let me go back and look. Maybe I have that date wrong. Let's see. So to go back to the slide, the next webinar is December 16th. So good thing I did. All right, December 16th. Postgres Enterprise Manager. Looking forward to that one.
Definitely. Thank you so much, Tom. Thank you so much, Bruce. Today's been great. We'll be sharing the recording and slides with you as soon as possible. And I hope everyone has a wonderful rest of their day.
All right. Happy holidays, everyone.
Bye.